November 1, 1952. It's 7:15 a.m. The trigger went off. An entire island in the Pacific Ocean was vaporized just in a second. It was Ivy Mike, the world's first thermonuclear bomb, powered by a fusion mechanism. What is fusion? Imagine two hydrogen nuclei. Both carry a positive charge, so they naturally repel each other. But if you give them enough energy, they can overcome that repulsion, also called Coulomb barrier, and fuse into a single helium nucleus. But the thing is, if you measure the mass of two hydrogen nuclei and then compare it to the new helium nucleus, it won't be exactly the same. There will be this tiny mass difference. That mass gets converted to energy, thanks to E equal to mc square. But fusion is hard. To push two positive nuclei close enough to fuse, you need temperature of at least 100 million Kelvin. That's insanely hot. But scientists were clever. They used a fission bomb, the kind that destroyed Hiroshima and Nagasaki. Fission doesn't require high temperature. Fission happens when a neutron hits a heavy nucleus, like uranium. The nucleus splits, releasing huge energy and more neutrons. So, for Ivy Mike, the energy released by the fission bomb raised the temperature to 100 million Kelvin, where fusion could take place. Scientists were very clever, but nature is cleverer. Our sun, or any star, is a fusion chamber. All the energy, warmth, and light that we get from the sun is a result of fusion. But do you know what is the temperature of the sun? You'd expect at least 100 million Kelvin because of course the fusion requires the temperature, but actually it's only 15 million Kelvin inside the sun's core. Doesn't it feel like the sun is cheating the system? Well, the cheat code is quantum tunneling. Suppose you are stuck at position A, and if you have enough energy to climb to C, say 10 units, you can climb there. But if there is an even higher barrier B in between, to reach C, you need enough energy, say 100 units to overcome the height B. So if you have just 10 units like before, you will never reach C. That's the classical world we live in. But the quantum world is strange. Tiny particles sometimes act like waves and sometimes particles, depending on the experiment. To connect the properties, a mathematical tool was developed, where each particle is assigned a wave function. The wave function is not the particle itself, but contains all the information about it. Its square gives the probability of finding the particle there if measured. For example, imagine this particle is trapped inside this line. By trapped, I mean it would take a large amount of energy for the particle to escape the situation. Let's say the wave function of this particle is this. It's not just made up, we get it by solving the equation that describe the physical setup or whatever. Here is a peak at the center. So, if you measure the particle, your chance of finding it in the middle is the highest. The probability decreases as you move away and so on. Notice how the wave function drops to 0 at the boundaries and is non-existent outside them. Since the wave function indicates probability, this means the chance of finding the particle at or beyond the boundary is 0. This is because the particle is in a hopeless situation, requiring an infinite amount of energy to escape. But what if the barrier isn't infinite? Then the wave function looks like this. You can see it's not 0 outside the boundary. It's just very small, but not 0. That means even if the particle does not technically have enough energy to escape, there is a tiny chance that it could appear on the other side of the barrier and be free, just because maths allows it. It does not mean that it has jumped over the barrier or tunneled through it. Even though the scientists call this quantum tunneling, it does not actually tunnel. So, what does all of this have to do with our sun? Remember the Coulomb barrier? The protons require energy to overcome the barrier, and the sun is too cold. It does not have the energy to give the proton the energy to overcome the barrier. But thanks to quantum tunneling, some of the hydrogen atoms overcome the barrier and fuse. And those few are enough to ignite the sun and all the stars in the night sky.